Are we sad or happy? You know what? Me too. I am gonna miss you guys though. But ending classes is always nice. So as I suspected, I did not put together any sort of final exam review. And then I thought, well, wouldn't it be kind of fun if we just did it together? So what I want to do is go through test 1 questions, test 2 questions, and then highlight things that you haven't been tested on yet that I would want to include on the final exam. Okay. Way back to test 1. We've tested things from test 1 kind of implicitly in the other tests, of course. But let's go back and I'm taking requests. If there's a question that you want on the final exam, then let me know. See something, say something type of deal. So the solutions are posted on Moodle if you want to follow along that way, or I've just got them here. Okay, so, and I'll tell you if I don't want it on the final exam for whatever reason, okay? And so some stuff we just touched on briefly and it's not final exam material. Off the top of your heads, anything from test 1 that looks good? Here we have a graph. You have to tell me if it's a function or not, right? It's good.
I like that.
Okay, can do. How about I'll highlight the ones and then we can revisit. Okay, I want about half the questions from test 1 and about half the questions from test 2. So the number of questions, and then some final stuff that you haven't been tested on yet, smoosh that on, and then there you have it. There's a final exam. So you've got a graph. You'd have to tell me function things. So is it a function? Is it one-to-one? What's the domain? Can you restrict the domain so that it is one-to-one on some domain? Usually there's multiple answers there. Evaluate the function using the graph approximately, and solve for x using the function. So that's a pretty good one. It's a nice warm up, right? How about, I don't want this one. Nah. Let's go, nah. Let's not put that one on the final. It's the same thing. That's why I'm not too keen on it. It's just doing the same thing, but with a table instead of a graph. I guess it's a little bit cleaner because the table was kind of hard to read, or I guess I picked a relatively good one. I'll have to remember to do that again. Write the piecewise function for so little space. It's quite a bit of work, right? Well, quite a bit, not a terrible amount, but I think it is a good question in terms of this function, right? You can just confirm that it's x squared, and the other ones were just horizontal lines, so nothing crazy, right? And once we've gone through these, right, we can come back and go through some questions if there's time. And so I'll highlight this one. Pretty fun, right? about that? And it satisfies the, can you look at a graph and figure out what function it is? All right. Find the domain. This one's a goodie. Why? I make you figure out if the domain, right? You can't divide by 0. You can't take the square root of a negative number. Those are all good things to remember. And so I'll throw that on there. I know I didn't check with you guys, forcing it on you. Although the next question is good, especially if you're heading into calculus, right? Then you'll be doing a lot of rate of changes like this from 2 to 2 plus h. So just remember that if you're going into calculus, and if you're not, then who cares, I guess. Was it good or was it not good? I can't remember actually. Usually I remember how you did as a group on it. Okay, this one's a maybe. I'll do maybe. We'll decide once we see how many questions we have. I'll come back and see if there's room on there. We do the average rate of change, right, on some interval when we find the slope, for example, right? It's just kind of a weird endpoint, 2 plus h, right? We've just moved h units out from 2. So we do it later on. Function composition. I'm sorry to say, we have to do it. But as long as you keep your head in the game, stay nice and focused, right? Evaluate the inside function first, the g of 5. You have to go to g. The input is 5. The output of g of 5 is 0. Now you take that and put it into f. The input into f is 0. So the output, the final output is 1. Yeah. So pretty fun once you settle down. Okay, increasing, decreasing. Do you want this one? I'm okay to axe it. Lukewarm, okay. Let's see here. So I give you a function. You have to tell me where it's increasing, where it's decreasing. Where is it concave up? Where is it concave down? Where does it have inflection points? I'll put a question mark. Lukewarm. I feel like that one was pretty good on the test, so, but that was a long time ago. Ooh, I forgot we had more domain questions. Could do this one instead of the other domain question. And then we could cut the table f of g of x, function composition this way. This one's a little bit more advanced. F of x is x plus 4 and g of x is the root of x plus 5. Feels like very similar to the other one, but f of g of x is what you have to find first, right? And then state its domain using interval notation. This one's a goodie, but then we could swap for 6 and 4. Kind of reducing the number of questions, increasing the difficulty a little bit, right? But testing both of the same things as the previous 2 questions. So that would be the trade-off. I'll circle this so I remember. I guess we'll have one of these, right? I tell you what the movement is. So give g of x in terms of f of x. If the graph of g is obtained by reflecting the graph of f, or some sort of transformations, a series of transformations, and you have to tell me what the final function looks like in terms of the original function. We also did one like that. I feel like we did another one. Okay, this one I'm putting on there, but I also remember it was quite good on the test, so I don't feel bad. Man, these are all good questions. How do we decide? Okay, so I give you a function which is squared. So now you know, okay, I've got this parabola and it's shifted to the right 6 units. And so you know what this thing looks like, right? Just by x minus 6 squared. You can find the domain where it's 1 to 1 and non-decreasing, which means it's increasing. So that means from 6 to infinity, right? And then find the inverse on that domain. I feel like that one's a bit rich. I might regret it. Oh well, I've committed now. Find the point of intersection between two lines. We are going to find intersections of a circle and a line. So we don't need to do this one. You can practice it, right? At the point of intersection of two lines, right? Then they have to be equal to each other. So you can set them equal to each other, solve for the value of x that makes that happen, and then use that value of x to solve for y, which you can obtain by putting the value of x that you found into the first function or the second function, because at the point of intersection here, there, so here, right, the value of x has to be the same and the value of y has to be the same for both functions, right? And we use that later on. So that's why I say no. That's like a baby version. We do a big kid version. This is a good one. Love this one. A line goes through 2 points. Find the slope of the line. That's the average rate of change. All right, so we crossed that off earlier. I knew we'd get to it later. This one's a good one. What's the slope of a line parallel to this line? So what does it mean in terms of the slope to be parallel or let's say perpendicular? Then find the equation of a line that's perpendicular to that line, passing through some point. You need to have some point that it passes through. We'll keep this one. Been a while though.
Is that just the negative inverse one?
Yeah, so if you have M1 or M1 is M1, whatever it is, then M2 is -1 over M1. Technically, M1 times M2 is equal to -1. Same deal. And of course, if it's parallel, then M1 is equal to M2. That one's easier. So you have to remember those. Do you want this one? The regression line? It is easy. Yeah. All right. Sold. That's got to feel good. Huh? Solve an absolute value equation. It's So where you had to take the positive and the negative version, right? And solve for it. Another one that we could do with absolute value functions is maybe find the horizontal intercepts of this function. So then I would cut this one and keep this one, which I'm leaning towards. I have to do one absolute value function. There, I'm forcing you into it. Whee! The horizontal intercept is when y is equal to 0. So you set it equal to 0, which you can convince yourself is the exact same type of question. Here you're forcing it to be 10. Here you're forcing it to be 0. A little bit more work, right? But the mechanism is the same, right? So we'll do this one because it looks better. Looks harder, but it's the same. We could do a mashup of these, right? Find the horizontal intercepts, because that's what you would have to do to find where it's greater than 6. Instead of the horizontal intercept, you're finding the intercepts at 6, and then you're finding the values. So maybe I'll alter this to be find the horizontal intercepts and where f of x is greater than 0 or less than 0. Some version of that. But then we can axe this, because they're the same, right? What did you have to do? You had to find the horizontal intercepts, which looks like this, right? And so no positive, let's see here, move it over, move it down, something like this. That's what it should look like, ish. You're going to find the horizontal intercepts, and then the intervals where it's greater than 0, well, that would be from here and then here, right? Or if it's less than 0, if that's what I'm asking for, then here's where it's less than 0. So you can use the test points, right? You can figure out here it's positive, here it's negative, and here it's positive again. Okay. It helps if you know what the function is going to look like, right? It definitely helps knowing that, okay, here I've moved it over by 4, and then I've moved it down 8, and then I've kind of smushed it a little bit, right? And then, but I didn't reflect that here, but, right, knowing what it's going to look like helps checking your answers. You don't have to. You can solve for the points of intersection without knowing what this thing looks like, right? And then you can use just some test points, right? Here's point 1, here's the point of intersection, the horizontal intercept 1, and then you plug in some values here, 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 right? You pick convenient values, plug them into the original equation. Is it positive? Is it negative, right? And then you can figure out the interval where it's satisfied. So that's a good one, but I'm mashing it up with, where is it, positive or negative? Huh? Test 1.
That's it.
That's it. That's all you'll need to know from test 1. We can move on to test 2. Yeah, before we revisit the question marks, let's go through test 2, which is kind of fresher, and see how many questions we get. Yeah. Any comments, concerns? Don't make it hard. I'm telling you what's going to be on there. Not the same numbers, right? But you've got assignments where I pulled these from verbatim. You've got practice for test 1. which were exactly the same. Can convince yourself of that. And you've got your tests, which you know how you performed in a test scenario on, right? So go through those and you've got it. Okay. Do the same thing for test 2. The harder stuff is going to be the later stuff that we did after test 2, which of course we have to test on. Describe the long run behavior of this function. Do you want it?
Yes, it's pretty easy.
Yeah.
That's what I thought. Should I do a mashup of this one and this one? Also relatively easy. I
Yeah.
find the degree, the leading coefficient, kind of warming you up into polynomials, right? So I'll do they're not going to be 2 separate questions. I'll combine them because we've grown up a little bit. But I think that's 5 marks in the bag, huh? That's pretty good. Give you a function with some missing coefficients. I give you the vertex. So in standard form, I give you the vertex. So you can use those to find B and C. That one's pretty good. I think, so I want this one, but I feel like I test a vertex question again. So I'm going to put a question mark, but I want it. That's like a smirk. That wasn't on purpose, the smirk. This one's pretty good. You have to find, I knew it. We could cut this one and do some version of the rocket launching or a ball's being thrown, right? Where the key is that I give you the function, right? That's nice of me. You don't have to build the function. I'm being very nice. The reason I like this one, right? You have to find the y-intercept, right? You have to find the vertex, right? Where does it reach its peak? Looking at this here, I see that I have a parabola, right? From the degree 2. I know it's been flipped upside down, right? And so it's being launched like this, and then it's going down like this, right? Those are all things that you know from just looking at that function, right? And so where is it being launched from? Well, that's whatever the starting point was, right? And then where does it reach its peak? Well, at this value of x, which you can find, right? And then you can find the height of it. And then what do I make you do? Oh, find the horizontal intercepts. Oh, sorry, I should make it the ocean. Right? At some time point, it's going to cross and fall into the ocean, right? Or land on the ground, whatever, they're the same. And so you'll find 2 horizontal intercepts, right? But only one applies because the other one's probably negative, right? Because if you think about just a generic parabolic function that looks like this, it would look something like this, right? Where here is where it's being launched from. And I guess I don't have that much faith in my rocket, I guess. I didn't let it go very high. right? So you would find two horizontal intercepts, but only one applies, right? And then you could figure out whatever the question's asking for. At what time does the splashdown occur? So at what value of X does it happen? You're translating that word problem into a horizontal intercept, which you know how to find, right? Set the Y equal to 0, and then you're good. Quadratic formula, obviously, parabola. Okay, man, what a good question. Kind of an adult version of the itty bitty domain one. Why is it more grown up? Well, because there's a quadratic inside, right? And so then you can figure out where it's less than 0 and that's excluded from your domain, right? This one's kind of a big question, and I'm okay to cut it because we test different components elsewhere, unless you want it. No, you got it. You can practice it because you need those. Oh,
It's just quadratic, and then when you get to 2 points, you can only have top of this one.
you have to figure out where x squared minus 8x is positive, right? Or equal to 0. So it's very similar to, it's kind of a mashup of this one, and then we did it with the absolute value, which is very similar. So we've already tested those concepts, right? And so you can use this one for practice because it'll still be useful. All these questions will, you're seeing, they're all basically the same, right? There's so many overlapping questions. I know you don't believe me, but they are. They're all just the same. All the same skills. Ooh, or do you want this one? A little bit tricky. I think once you figure out that you have to count the t's, right? T to the 3, t to the 2, and t to the 1, 3 plus 2 plus 1, right? Then you have a power of 6, right? An overall power of 6. And which is even. So then you know it looks like this. There's no reflection. You have to check on that. All right. I'll only do one long run behavior question. Do you want this one or the first one where I just give you the polynomial? First. Sold. The first one's a nice warm up. I make you do the degree and the leading coefficient, and that's a quick win. And in my mind, this is the same question, so I only want one of them. Oh, bummer, guys. Of course, you're allowed to use synthetic division if you want. We didn't cover it in class because I only want to give you one way to do it. And so I use long division, but if you read the textbook and you prefer synthetic division, that's totally fine. But you will need to show me that you can divide a polynomial by some very simple function, right? A linear function. I'm not going to get crazy, right? It's going to be either some version of x plus a, right? Not even ax plus b, right? Just x plus something. But if the something is negative, then it's minus, right? But very, very, very similar. Yeah. This function will change, this function will change, but you've got it. And I remember this one was very good. So I don't feel bad. Hmm. Hmm.
I don't like that one.
Yeah, I'm not too keen on this one. The domain is going to be super basic, so I'm not really interested in that anymore. The y-intercept is where x is 0. That's just basic algebra. The x-intercepts, well, that's fine. You set it equal to 0, but you can just retrieve it from here. Where does this thing equal 0? At -8, and 5x minus 8 equals 0, right? The vertical asymptote, nah. Don't worry.
I would rather do that than the one that's coming.
I know. I'm really locking it in before I scroll down. Nope, it's game over, guys. So this one, right? I give you a function, and then looking at different discontinuities, right? What does it mean for it to have a vertical asymptote at some value of x? Well, that's when you do your cancellations here, and you find that there is still some function of x, so some value in the denominator where you're dividing by 0. So that would create a vertical asymptote, whereas a whole is when you've managed to cancel these things, right? Notice that they're the same. So you look at the powers, right? And all the numerator powers are higher than the denominator. So that made all of these wholes, right? Kind of being nice, but I can mix it up, right? And so if something cancels, let's say we change this to nothing, right? Then you could cancel one of these, right, with this, but you'd still have x minus 2, and then this one is going to cancel, make 2, this one's going to cancel and make 1, and this one's going to cancel and make 1. So when this happens, right, when they're still there in the original function, but when you're able to cancel them out, they make wholes at these values of x. X equals 4, x equals 7, and x equals 10. This, when it's still there in the denominator, where there's some value of x where you could end up dividing by 0, that's where you have a vertical asymptote. Okay? And so
it's still a whole if they both perfectly cancel as well, right?
Yeah. If it's kind of disappeared from your simplified equation, then it's a whole in the denominator, right? Not necessarily in the numerator. But this is the original function. So all these properties are still there, right? It's just whether this value of x equals 4, for example, has been kind of canceled out, then it's just a whole. Or if it's still there, x equals 2, then it's a vertical asymptote. Yeah. There's a lot of marks riding on you knowing, right? I'm more interested in that for test 2, maybe not so interested on the final exam, unless you want to show off. You still have to know what it means to be a vertical asymptote and a whole. So I'll.
Yeah, it's 3 marks.
Yeah, it's a lot of marks.
Oh, you want it?
Yeah, I'm not sure.
Okay. Can do.
I didn't watch the videos. So I was like,
Well, that sounds like it's on you. But now, and this, I guess this is a good time to remind you that as long as you do better on the final exam than one of your tests, I'll shift your lowest test weight to your final exam, right? I'll just pretend you didn't show up, And there you have it. So as long as you're improving, that's my goal, okay? I don't think anyone can argue with that. So that's what I'll do, right? You've got a chance to redeem yourself. Oh, exponential decay.
I like those.
Yeah, it's a good one. Okay, we'll use it as a warm-up. We do more advanced things, so that's why I was kind of tempted to cut it. But you know what? Sure. I like this one. An exponential function a times b to the x passes through 2 points. Find the formula for the exponential function. I would like to have this one there, but we'll see if we have room, so to speak. No? Do you want it? That's a question. Oh, well, this one's nice because I give you when x is 0. So then x is 0, you can solve for a is 3,000. So then you have a, then you let x be 3 here, and you know the output is 2187. So then you can solve for b, and then you can assemble your f of x as a times b to the x. Pretty good. Okay. You got me. I love that question. Oh, the monies. Unless you want it, I'm okay to cut it. Basically the same as the car depreciation, except we're appreciating, right? Unless you've taken out a loan, then you're appreciating in the wrong way. We'll cut this one. Mostly because I don't want to use up all this space giving you the formula again. Nah. Oh, and I'll extend it to, whoops. The continuously compounding, right? E to the x, but, or e to the kx, I guess. But we'll see that later, so it's okay. Pretty sure. Here's the one I was thinking of that we could do instead of that transformation one where I give it to you in words, right? So construct g of x where from f of x where it was shifted to the left and right and whatever up down reflection. We could do this one instead, or some version of this one instead, if you prefer. I'm only getting one head nod. Let's see, it was on test 1. So you're choosing between, I feel like an optometrist. 1 or close your eyes. Or where is it? Nope. 2. To me, these are the same question. I know, not cool, right? Test 2 instead. You had to remember that it passes through 0a and 1ab. That was kind of a key, right? But besides that, yeah, so that's why I guess I'm kind of leaning towards this one because it is on your formula sheet. Okay, yeah. Sold. for practice though. They're all good for practice. Oh, these little cuties. Write an equation in exponential form, in logarithmic form. I think these are kind of quick wins. Yeah. 1, 2. This one's the same in my mind as the previous ones. So maybe I'll do some version of this here. I don't know. Nah. Can do it for practice, but it's just using those inverse properties, and I think that's kind of boring because we use them later on anyways, right? When we're solving things. Okay. Solve for t. You have to move things around and then use the log to bring the t downstairs. But besides, after that, you're off to the races. I'm feeling pretty good about this one. Or do you want the one with the quadratic instead? No. You know what? I had a feeling. I think I had two. Oh no, this one was just right as a single logarithm. I could do that as part of these quick wins up here. Right. I'll do a mashup. I'll make a note kind of with 14 and 15. Might just make it 1 mark though. It's really easy. I think sometimes I inflate some marks because I know that got it. And even when I'm marking, I feel like there are some marks that I would never take away. They're not in my grading scheme. Because you always start at 100, right? And then I pick away at as I find errors, right? You don't have to build up to full marks. You start at full marks and then I chip away, which I think is nicer. But that means there's always some that I just don't chip away from. So that's why I do it. Ooh. This one's pretty good. I like this one. It's very similar to this one though, right? And you know what? Yeah, I'm gonna cut the next one. It applies the same methodology, right? You take the log to bring the x's downstairs. You have to do it to both sides, right? And then now you're stuck with 9x minus 5 times the log of 8 times, or is equal to 4x minus 10 is the log of 10, whatever log base you want. And then you have to rearrange and solve for x. Nah. We do that later anyways. Similar. Solve for x. Dun, dun, dun. You have to use those log properties. This one's pretty good. Although it's kind of been played. Right. Simplify by combining the logs, right? If you're adding logs or subtracting logs, then you can multiply or divide inside the same log, and that's how you're going to combine these, right? So I am testing that simplification, which means I guess we could ditch this one just to reduce the number of questions. Let's do that because they're the same, right? Log base 7 of something plus log base 7 of something.
Did you just do that one quick for review?
This one?
Well, no,
or the next one?
Beyond there.
So this one, wait, where is it? Here. Sure can. Okay, so here you've got log base 10, and here you've got log base 10. That's the first thing you want to check, right? Is that you have the same base. If you have the same base, then the log properties say that if you're adding logs, then you can combine them and say that this is the same as log base 10 of x times x plus 1 is equal to 6. Right. Which is what you would be doing in the previous question, but that was basically the end of it here, right? Log base 7 of 3x to the 8 plus log base 7, you have to check that they have the same base of 2x squared. Then you can combine these and say that the log base 7 of 3x to the 8 times 2x squared, right? That's the same move. So that's why I'm cutting it, because I make you do it in a bigger way in the other question. And then you can simplify these exponents, right? 3 times 2 is, let's do this one first, I guess. Log base 7, 6x, 8 to the plus 2 is 10. Whereas this one, x squared. So I've got the log of x squared plus x is equal to 6. I want to solve for x, which means I need to get at what's inside the log. Log base 10, if I raise it to the power, or 10 to the power of both sides, 10 to the log of x squared plus x is 10 to the 6. You don't want to forget that 10 to the 6. It's going to make a huge difference. Then I do that because then I can cancel, and the x squared plus x is equal to 10 to the 6 drops down. As soon as I see an x squared, I'm happy, because then I can use the quadratic formula as long as I set it equal to 0. So then I have x squared plus x minus 10 to the 6 is equal to 0, which now this is a quadratic. So now you've got x is negative b plus minus the square root of b squared minus 4ac over 2a. That old gambit, can I say that? I don't know. Negative 1 plus minus the square root of 1 squared minus 4 times 1 times negative 10 to the power of 6. Yikes. 2 times 1. I think this becomes something. 1 minus bracket 4 times 1 times 10 to the power, oh, sorry, negative 10 to the power of 6. Let's see here. Get the root of 4001, which makes sense. Oh, sorry, more zeros than 4,000. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 1. Divided by 2. The root of that, the rutabaga. Negative 1 plus minus. It doesn't even give me a nice simplification. Some value. I get 2,000 this time, 0.00025 divided by 2. I'm going to store that. So x is, I shouldn't have written so lofty initially, and I need more room. Negative 1, I'll do minus that previous answer divided by 2. So I get negative 1,000.500125, or x is negative 1 plus shift recall a divided by 2. 999.5000125. Now, on test 2, because we were just starting, I wasn't very mean about the domain of the logs, but on the final exam, we've spent enough time in the logs to know that I can't take the log of anything less than 0, right? Including 0. And so, so now if I look at x negative 1000 here, you have to think about your domain as well, right? So x has to be greater than 0 and x plus 1 has to be greater than 0, which means that x has to be greater than 0. Right? And so now this one can't be since x is greater than 0, which means that this is the only answer. I hope I was nice. If I was mean to you, I probably made a note, right? Oh no, you have to cut this one. But I remember being impressed that a lot of you remembered that, okay, can't have a negative, so then there. Oh. Nice. How are we doing? Oh, good. New stuff. Word problems mostly. Uh-oh.
Could we use the quadratic function on our calculators?
You can tell me that you're using the quadratic function on your calculator, or like on calculator, this equals this, this equals this. That's totally fine. I'm fine with that. As long as you're telling me what you're doing, yeah, use whatever you want, I guess. The new stuff started on November 22nd. And we did kind of briefly talk about, well, we had already talked about the domain of a log before the test, so I'd introduced it ahead of time. And then we looked at the graphs of logs, but we found the domain of logs, which I'm already testing, so nah. Transformation of logs, clearly I didn't want to do any of that. And so, nope. 4.6 though, that's where all those word problems are, right? And so let's pick, or let me find a good word problem that, let's see here. Oh, my erratum. Hey, where's my pointer? There. Well, probably can't have that one since I messed it up. Population growth, they're all the same. How about a Newton's law of cooling? That's a nice show-offy one. I'll give you the formula. That's what final exams are all about, showing off. We could even do a turkey.
I do like that. I mean, could you just go back to the formula?
Yes.
It says, oh, never mind. Because I think I wrote down in my notes that A was the initial temperature, but it's not. It's a constant.
Yeah, so unlike the other A's, because there's the surrounding temperature, it kind of messes with it a little bit, right? And so A is not necessarily the initial temperature, but it's a constant determined by the initial temperature because you set T equal to 0, and then you're able to solve for, so then this e to the kt goes to 1, so then you have A plus the surrounding temperature, which I have to give you, is equal to whatever the temperature is at time 0, right? And then you'll have A in a roundabout way. Okay. So as a way of indicating, I'm going to add it to my test 2 list here. This is more for me than for you, I guess. Hey, paste. There. There was a turkey. There was a dead body. I think the turkey's nicer. There's a classic coffee cup one, but I don't think I assigned that one. It's the same, but how about a turkey? No, we want the dead body one. No, we'll do a cute turkey. Right, some surrounding temperature. It's coming out of the oven at some temperature. Right. Okay. Let's see here. What was nice about the dead body one is that you had to force a time equal to 0. But it's a little bit harder than I would expect on a final exam. So we'll stick to a turkey. Let's see here. So some version of this. And I think that's all we did that day. Oh, that was the 22nd. How about the 24th? Oh, magnitudes. That one's a good one. Should we do an earthquake one? Why not? It's going to be hard for me to test anything about the log scales, but we'll do one of these.
And is that thing gonna be on the formula sheet?
Yeah, I'll give it to you. Yeah, so anytime, yeah, I'll give you this, I'll give you this, well, and this, obviously. I'll give you those. I guess I'll give you the entire blurbs. This makes it look like I'm only gonna give you those, but I'm gonna give you this and this. And oh, I guess I was using green for unknowns, so I'll switch this to blue. So, and this one's gonna be an earthquake one.
How did that one work with, we had that one question that we kind of didn't finish at first, we kind of got the magnitude, but we didn't.
Oh, yeah, because I threw in the towel.
Yeah.
There, that's done, but here, 4.5 times more energy is the order of magnitude. So then you have to take 10 to the whatever you find at the end. So I added it after the fact. If it's in red, it's after the fact. That's sneaky. Yeah, fitting exponential models to data. We did that Excel. I mean, this is a good exercise. I'm not going to test you on it, right? But showing that if you take the log of an exponential function, it becomes a linear function, right? So that's good to know. And that's what you're using when you're using that log paper or whatever it's called. Or Excel, probably. 24th, followed by the 27th. Oh yeah, here's the dead body. But we decided to go for turkey, so this one's good practice. Here's an earthquake practice again. And then we did the flow duration analysis, which I'm not going to test you on because it's not my field. So that would be weird. Oh, circles, circles, circles. Yeah. But to really show off, we can make it an angle. How about I promise I make it a nice intersection? Or nice intersections. Equation of a circle, equation of a circle. It was all building up to. I guess this one's kind of cute, but it's the same as the ant one. All right.
Is that the 45-minute one?
No, that's the ant one, I think.
Yeah.
Yeah, so then I gave you this one and said, hey, we'll do it next class, and then the projector broke. But I did make the solutions and I posted them on Moodle. And so, and I feel like it's pretty good. Let's see, your projector wasn't working. So
It sucks, it combines like almost everything. Yeah, I think
the voice of reason. It's good. Instead of doing a bunch of kind of the same stuff, just cuts to the chase, right? You have to make the equation of a circle, find intersections of a line, right? It means that we can cut the intersections of two straight lines from test one, because we're doing it more advanced here. And look at how cute. What I'll do is I'll include some graph paper or like a graph paper snippet so that you can have a proper scale so that you can see it. Right, because that's going to be helpful.
So there's no video of when we did this, like step by step.
No, just the solutions, kicking it old school. It probably exists somewhere. I'm sure David Lippman's gone through it and has a video somewhere, but I don't have one. But I did talk you through it in the solutions that I made after class. So we want to find the distance from A to B. So the question is, an ant is heading toward a circular region of pancake batter, and the ant cannot breathe while walking through the batter. So then we know, okay, the batter has a radius of 4 centimeters. The ant is going to walk from a point 6 centimeters due north of the batter's center to a point 5 centimeters due west of the pancake center or the batter center. If the ant moves at 0.8 centimeters per second, we'll parking lot that information until the very end. How long will it have to hold its breath? So we sketch out the scenario, say that as if it's easy, it's not, right? But we can draw a circle with radius 4, centered at the origin is the easiest way to do this. Okay. You could get crazy and center it somewhere else, but it's going to make the question a lot harder. The final answer is the same, right? But it just makes it harder. So center at 0, 0 at the origin, and 0.06 through to -5, 0. So now we want to find the distance from A to B, right? Because that's how long they'll have to hold their breath. Okay. So that means that we need to find the intersections of at A and B, which 2 intersections. First thing we do is find the equation of the circle. Right, that's going to be useful. Find the equation of the line. We know how to do that, right? I have 2 points on the line, the outside points, right? And so I can find the slope of the line. I can find the y-intercept. So I have the equation of the line. I have the equation of the circle. And then we're off to the races. So here I found the equation of the circle. Then we can find the equation of the line of the ant's path by finding the equation of the line through 0, 6 and negative 5, 0. I guess you will have a recording of it, sort of, just walking you through it. You can find the slope, right? And then we know that 0, 6 is the y-intercept. So then you can construct your equation of the line. This fraction was a little bit nasty, right? So that's something that I'll avoid, right? Make the slope something reasonable, right? Not a fraction. Fractions are reasonable, but you have to be nice and methodical about it. Okay. It's more of a practice question, right? At the intersections of the line and the circle, we can substitute y equals, so the line, into y in the equation of the circle to solve for the values, because we can see that we're going to have two values of x where this is true, which make it true. So I've got my equation of the circle, which we had to construct, right? Centered at 0, 0, making it nice and simple. And then I put in the y value for the line, right? Y equals 6 over 5x plus 6. Then I can expand that, making sure you're careful about your expansion. Here we got a little bit riddled with fractions, right? So if there's no fraction in the slope, then this would be a lot easier, right? And then if I expand this out, I get a quadratic. I set it equal to 0 so that I can use the quadratic formula, or your calculator, totally fine. I went old school, right? You can confirm that you get the same values, sticking with the fractions, right? But if you don't have fractions to deal with, then you're fine, right? And so, and I promise you won't have fractions. It's good to practice with fractions, but you won't have fractions in the end. So then after all that fraction work, I went and used an approximation. Oh well, whatever. And I stored these values so that I could use the entire value. So I'm not actually using the approximations, I'm using the exact values, but just so we can see roughly where these are, because I don't know about you, but negative 360 plus 20 root 19 divided by 122 doesn't mean anything to me, but negative 2.23 does. So in terms of figuring out if these values make sense, right, then I can look and say, okay, yeah, negative 2.24 and negative 3.67, those values make sense on my graph, especially if you have the axes like this grid paper that I'll give you, right? Then you can really confirm, right? And so now you have the values of x, so close, sort of. We're like 2/3 of the way there. So then use the x values to find the y coordinates, right? You can use the circle equation, but that's going to be a lot more work than using the line, right? You're plugging in those values of x and solving for y. I would much rather plug it into the line than the circle. You can try both, because at the intersections, they have to be the same, right? So then I plugged in these values, and how I showed that I use the exact values is I just wrote store A and store B, and you can do the same, right? If you've stored something, tell me where you're storing it, and then you can just refer to that in your work, totally fine. And then I get the approximate y points, right? 3.32 makes sense, and 1.6 also makes sense on my graph. Now, the extension, right? So now I have this, so I trace this and I moved it over here. I can find the length of the y side of my triangle, right? And use the Pythagorean theorem, and I can find the length of the x side. And here, yeah, you're okay to use just the approximations, right? You can round to 2 decimal places or something. And then unless you want to show off and store the values, that's great. But I did not, I got lazy. So then I can use the Pythagorean theorem to solve for the length of the trip through the batter where the ant has to hold their breath is roughly 2.17 or 0.18, I guess, centimeters at a speed of 0.8 centimeters per second. That means that it's going to have to hold its breath for 2.725 seconds-ish.
That's worth 40 points.
It'd be a solid 8 to 10 marks.
So I should just study this instead of the rest.
Pretty much. If you can do this, the rest will be easy. But this individually, the concepts aren't terrible, right? But it is a nice way of kind of smushing it all into one. Would you want me to break it up into parts? No, just go for it. Give you an entire page to work on and just let loose. You don't even have to draw it out if you don't want to, but I find that it's helpful. Okay, the pancake batter. I think what you'll find is me explaining it takes a long time, but you doing it doesn't actually take that long.
That's a bold assumption.
If you've done it like 4 times, right, change some values. Oh, what would be a good exercise? Mapping it backwards, right? To figure out what values, where would it have to start and finish? What would the radius have to be? Or what could the radius be? If it's still walking through the batter, but you want to get a nice slope, that would be an excellent exercise for you to try. You can vary the speed, but that doesn't matter, right? It's only the numbers that are going to change, right? So think about what would make, it's these 2 points that are making a mess. Or sorry, these 2 points, 6 and 5. These are the pickles, right? I could change the radius if I feel like it, right? As long as it works with the rest of them, right? But how would you change the 6 and the 5 to make it an easier to solve problem, right? Then you'll know what the question looks like. Okay. The projector wasn't working. Then December 4th. So when we did the tiniest bit of trig, and we worked up to sine and cosine. I feel like there was another day, or was there no other day? Yeah, and that's the one I want.
Yeah, that's the last one.
Yeah, was there one in between? Oh, November 29th. Did we do that one? Oh no, that's when I gave you that one to think about. December 4th. And today's this, I guess. Started talking about angles. This is when we went canoeing, and that's the one I want. A boat, a canoe. paddleboard. I'm gonna use some fixed object, the radar, or a lighthouse, or maybe even a buoy. I don't know, whatever. They're all the same, right? And so here we've got a boat problem. A boat problem. Using trig. And that's it. It's pretty good.
And on that one, the distance away is always the hypotenuse, right? Is that-
Yeah, because it's gonna be at an angle. So it'll be the hypotenuse. In fact, I guess we could decide as a group. You're gonna have a fixed point here. You're gonna force it to be the origin. Where on here do you want your watercraft to be? Say when? Quadrant 1, 2, 3, 4.
It doesn't matter.
I know it doesn't matter. Quadrant 3. You're crazy.
Then you have
Yeah, we did that.
I know, we did do an example. There. Here you're gonna have your boat, maybe a sailboat. Whee! It'll look something like that. Which we did an example of. What perfect timing. And if you know all those things, then you did it. You conquered it. Any questions? All right. Good luck studying, and I'll see you next week at the very latest, I guess. Yeah, Friday, right? Yeah. Yeah.
So the exam is just like a written exam. Tutors and-
Just a paper, just like the test. Yeah, I know. Stop this.
A finished thing of like